Evening viewer, welcome to our Glory Globe TV. Here's the breaking news. Yes, spinal cord. The spinal cord is harder to access and study than even the brain. The challenges posed by its mobility and anatomical structures have made understanding exactly how it functions difficult. Rice University engineers will work with collaborators to optimize an array of nanoelectronic threads or NETs already used successfully for gathering high fidelity long term data from neurons in the brain for use in the spine, supported by a 6.25 million Fourier grant from the National Institutes of Health. In addition to neuronal activity recordings, net probes can provide tunable, localized stimulation of adjacent neurons. Rice neuroengineers also hope to maximize NET's functional bandwidth by integrating them into a larger scale data processing systems. The new tool could help neuroscientists crack the secrets of spinal cord functions and bring new hope to patients dealing with injuries and other associated medical conditions. Using electrodes to track neuronal activity in the brain has allowed neuroscientists to learn a great deal about brain function. The flexible NET probes developed by XIE and collaborators integrate seamlessly with brain tissue and perform better than rigid probes when used to record electrical information from individual neurons in the brain. Preliminary tests have shown that NET probes can achieve high quality, long duration recordings from spinal cord neurons of mice. However, the scientists intend to further adapt NETs to the specific structural and functional demands of the spinal cord. In the brain, the distribution of neurons or grey matter and the bundles of nerve fibers known as white matter is the exact inverse of spinal cord anatomy. We typically refer to this as the inside-out anatomy of the spinal cord, said Lan Luan, an assistant professor of the electrical and computer engineering and co-investigator on the grant. The outer layer of the brain, the grey matter, is where the neurons are, whereas the fibers called white matter are on the interior. In the spinal cord, the white matter or fibers are on the exterior, shielding the neurons. This makes accessing those neurons more challenging. To ensure better access, scientists plan to develop a probe design that is small enough to be implanted at different sites on the spine yet has greater depth, coverage and enough channels to capture data from neurons in a spinal cord cross section. Another goal is to equip the probes with stimulation capabilities in addition to their recording function. The electrode can do both, Luan said. This has a direct health relevance because for patients with spinal cord injury or other types of injuries, stimulation could be a way to restore fine motor control. There are several very successful technologies demonstrating that stimulation in the cord can restore local motion and also the motion. But to impact finer motor control, we believe we need to go inside the cord and have a greater degree of access and precision for applying this stimulation. The spinal cord plays a significant role in pain processors, so identifying which spinal neurons are directly involved with pain signal relay could open the door to better pain management therapies. Identifying the specific type of spinal neurons that play a significant role in processing pain information could potentially enable the development of drugs and target precisely those cells. Z said, or maybe we can use the electrodes to stimulate those neurons and modulate their activity so that they don't convey the pain signal to the brain. Scientists plan to not only optimize probe design but also to incorporate spinal nets into an extremely miniaturized integrated data processing and stimulation feedback system. In addition to developing the technology, Z, Luan and their team have partnered with the POP lab at the Salk Institute for Biological Studies, the Weber lab at the Carnegie Mellon University and the Basabalam and Ganguly labs at University of California, San Francisco for a series of spinal cord studies that will test the devices across different spinal regions, animal models and research topics. My real hopes that 4 years down the road at the end of this project, neuroscientists will be able to see and do new things that are impossible with current technology. G said. Behind the report, Glory Globe TV, Delhi, India.